Okay, welcome back for probably our shortest video of the series. You'll be excited for that. This is the one extra example that I said in the last video. We'll just come back and do separately. This is our last example in section 11.8 power series. We're getting close to the end. So let's just jump right there. What are we going to do? We're going to redo an example in the book, example 4. In the book, we're going to do it with root test. The book does it with ratio test, okay? And we're going to do a little more complete job with the endpoints, making sure you're aware of what I'm looking for when I'm looking at your written work that you submit for written parts of the exams. For example, the final, the written part of the final. The final will be similar to test 2 in that we'll have an online portion and it will have a written portion, okay? So really what you ought to do right now is just write down this problem, the sum n equals 0 to infinity minus 3 to the n times x to the n divided by the square root of n plus 1. And then you ought to try to do it on your own without looking at the book with both ratio test and root test, okay, just to get the original, the first main interval before trying the endpoints. Then give the endpoints a try on by yourself. And then come back to the video and see how close your work was to what we're about to do, okay? And then you can look in the book for the ratio test version, okay? One clue that you are on the right track, at least, is if you end up with the same, at least interval without the endpoints with both the ratio test and the root test. If you end up with something different, then you definitely did something wrong with one of them, or maybe both of them. Anyway, all right, we ready? You ready to jump in? Have you stopped? Have you come back? What is it? I don't know. So maybe you've stopped the video, you've come back, you've made your attempt. Let's see how it goes. So again, let's just first remember why this is a power series, right? It's a power series because it has a sum, n equals something, 0 to infinity, of coefficients, c sub n's, constants, right, for each specific n, times x to the n, right? Okay, this guy is a power, ouch, I just whacked my shin into this, oh, that hurt. Okay, this guy is a power series about x equals 0, right? Or a equals 0, right? Expanded about a equals 0 because x to the n is really the same as x minus 0 to the n, right? So we're in powers of x to the n instead of powers of x minus some non-zero a to the n, right? Let's just keep going, right? So what are the CNs in this problem? Okay, just to make sure you're kind of getting the difference between what we were doing again back in the previous sections, 11.6, 11.5, which you have a quiz coming up on, right? In those sections, you didn't have an x to the n in general, right? You had just something that looked like that. And for each x that we put in, then, you know, for each specific x, then this just becomes a constant, right? And the question is, does that series converge? Now we're going to do it for infinitely many x's all at one time, right? Instead of doing it infinitely many times. That's the beauty of math, right? Okay. So, here we go. You ready? Did you come up with your idea? All right. What does the question ask? The question is asking to find the interval of what? Yeah, good. Convergence. How do we abbreviate interval of convergence? Good. IOC. Yeah? Okay. What's the other math word that's one word? It's essentially what we're talking about when we say find the interval of convergence. What is it? What's the domain, right? What x's can we put in so that we get out one and only one finite real number, right? What's the domain? What's the interval of convergence? Okay, so let's get started, right? We're going to do this one again with the root test because, as I said, the root test can be a little bit faster, quicker, slicker with a lot of these types of problems. We've done a lot of ratio test problems. The book has a lot of ratio test examples. Let's go with the root test. All right, so we're going to do the root test. Because, right, what is this? It's a root test for absolute convergence. Ooh, I just got out this nice new marker. You see how beautiful that's writing? It's a root test for absolute convergence, yeah? And so what do, right? This whole guy, right? The whole thing is in the role of AN from section 11.6, right? Okay? And so what do we do with the root test? We look at the limit as n goes to infinity of what? We take the absolute value of our guy AN, because it's for absolute convergence, right? We know what that means. And then we do what? Take the nth root of that, right? Okay? So here we are, we're all set up. And so let's just plug in our AN, right? So let's just get started. This makes our life simpler. The more you write stuff down, the better off you are. Again, I like to see the limit. If you're not telling me you're doing the limit, then I don't know you're doing the limit, right? Make sure you're being complete in your written work, okay? So here we go. Absolute value of minus 3 to the n, x to the n, over the square root of n plus 1. And then we're going to do that to the 1 over n, right? Okay, so let's think about this guy. We have a product of two terms on the top and then divided by another thing in the bottom, right? We can slap the absolute value around each one of those guys, right? Absolute value this, absolute value this, absolute value denominator, yeah? And what guy doesn't need an absolute value? Which one of those three things we just talked about? Which one? Yeah, the square root of n plus 1, that's positive, right? What comes out of a square root? Only positive things, right? Or 0, but and starting at 0 here, right? So only positive things are coming out of there. All right, so what do we have? The denominator is the square root of n plus 1, right? Okay. Let's keep our 1 to the n out here, okay? Or sorry, our 1 over n, our nth root out there. So, and let's make sure we understand dealing with the absolute values, yeah? Okay, and so I'm going to have the absolute value, right, of negative 3 to the n, and that's going to be the same as the absolute value of negative 3 to the n, yes? Okay, and that's going to be this, so let's just put that in there, the absolute value of negative 3 to the n, just so you see it there, right? Okay, so all I did was rewrite that as that, with my absolute value from out here. And then tell me about x to the n. What am I going to be writing? Yeah, absolute value of x to the n for the exact same reason. Replace negative 3 with x. Yes? Okay? X can be negative, right? We're saying of all possible real numbers, x. So x could be negative. So here we are. Now we're in a really nice place to start using rules of exponents and applying, again, this nth root, this 1 over n, has to go to each guy, right? It goes to that guy in the product, that guy in the product, and then that guy down here in the denominator, right? Okay, and so when we do that, what do we get? This becomes the limit as n goes to infinity. You guys tell me, what am I going to have up here, right? Okay, I'm just leaving this there just to make sure, just to highlight the need for the absolute value. Absolute value of negative 3 to the n to the 1 over n is the absolute value of negative 3, right? The absolute value of x to the n to the 1 over n is the absolute value of x, right? And then what do we have in the denominator? The square root of n plus 1 raised to the 1 over n. Yeah? Okay, what's the absolute value of negative 3? I'm sure you would have dropped this a while ago, but the absolute value of negative 3 is good. 3, good. Okay, limit as n goes to infinity of what? 3. Can I drop the absolute value around x? No way. No way, right? All over what, right? The square root of n plus 1 to the 1 over n. Okay, well, we have a little bit more experience, again, with doing this. We've seen a couple of examples. So the square root of n plus 1, how can I rewrite the square root power? Yeah, it's that to the 1/2 power, right? Yeah, that's a power, not, right? That's a power. Yeah, you good? Okay. And then what am I going to want to do? I'm going to want to swap those two guys, yeah? And that's rules of exponents, and that's legit. We're allowed to do that. So what do we have? N plus 1 to the 1 over n, right? All to the 1/2 power, or the square root of this guy. Yeah? Where's our n's? Are there any n's in the numerator? N is moving, right? This is how I know you know. N is going to infinity. Up here, there are no n's. So as far as n is concerned, this numerator is a constant, yes? Okay? So the whole thing depends on what does this limit go to. So our big question becomes, what is the limit as n goes to infinity of n plus 1 to the 1 over n, right? Because once I know what that limit is, then I just take its square root, yeah, and then I have what I have, right? Anybody have a wild guess? What do you think the limit as n goes to infinity of n plus 1 to the 1 over n is? Wild guess, wild guess. What do you think? Yeah, I hear it out there, yeah. 1, good, right? Have we shown that? No. So, you should be able to show it. What did we show? We showed that the limit as n goes to infinity of n to the 1 over n is 1. Very nice, right? Okay. And we already know, right, that the limit as n goes to infinity of any number, a constant, right? So let's write that guy. The limit as n goes to infinity of a constant to the 1 over n is 1, right? Because if our constant is non-zero, right, then what's happening? It's a constant raised to the 1 over something getting huge. A constant raised to 0 is 1, right? That one's super easy to show. This one required doing what, right? Natural log and L'Hopital, right? Yeah? Okay? This one would be done the exact same way. There's one more that requires natural log and L'Hopital. We talked about it before. The limit as n goes to infinity of what? Natural log of n to the 1 over n. Okay? So it also requires natural log and L'Hopital in order to be able to show that this guy is, what do you think? Also 1. So those are great things to have in mind when you're doing root tests. So this guy is going to 1 once you convince yourself of that. Yeah? And therefore, what is this limit? That goes to 1, right, as n goes to infinity. So what is this limit? Well, this limit is just, the numerator has no n's in it, so the numerator, limit of a constant, as far as n is concerned, is the constant. So the numerator is 3 times the absolute value of x, right? And what's the denominator? The square root of 1, right? What's the square root of 1? 1. So what do I get? 3 times the absolute value of x is my limit from root test. Yeah? Okay. Alrighty. You should also have gotten that out of your ratio test, had you done ratio test. Now, what do we do at this stage, right, once we've actually computed this limit, when we're looking for an interval of convergence, right? So, again, thinking back, because you have a quiz coming up on 11.6, right, and 5, but the 11.6 piece, right, if there wasn't an x, which you don't have in 11.6 problems, then this would just be a number, right, that comes out. And whenever the number is, you compare that number against 1 to make your decision about convergence, divergence, or inconclusive, right? But now it's something with some absolute value of stuff in it. And so what do? If we're interested in the interval of convergence, we want to know where it converges, right? And so what does the root test, what do you look for with the root test for convergence in the result of this limit? Yeah, good. You want this to be less than 1. Less than 1, we have convergence, right? If that's greater than 1, then what do you have? Divergence, right? And if it equals 1, what does the root test tell you? Nothing, right? Absolutely nothing, right? Inconclusive. You got to do another test, right? So this problem's awesome because it puts everything all together in one. All right, so what do we have to do, right? This is what we end up with. Now we have to solve this inequality. Solve the inequality for x, right? And so hopefully you're pretty good at these inequalities now. here just trying to erase my new marker. Hopefully you can see. All right, so we're going to solve this inequality for x. So what should we do? You tell me. What's the next thing to do? Good. Divide by 3 first. You want absolute value of x isolated, or if it's an absolute value of x minus a, you want to isolate that. So we divide by 3, okay? The absolute value of x is less than 1/3, right? Yeah? And now what? I've got absolute value of a thing less than 1/3, right? Okay? Again, remember, that's saying the absolute value of x minus 0 is less than 1/3, which says what? Let's visualize it, right? The distance between x and 0, right? Because that's the center of this series. X and 0 is smaller than 1/3, right? So here's 1/3 to the left, and then to the right is minus 1/3, right? Yeah? I can go 1/3 away. So what is the radius of convergence for this series? The radius of convergence? Radius of convergence is 1/3, right? I can go 1/3 in radius, either direction, right, when we're one-dimensional, away from 0, yeah? What do I know, right? Now that's visually, what is this inequality equivalent to? Right, minus 1/3 less than x, less than 1/3, which is exactly what we just talked about there. So what do we know? We know that from there to there, we have convergence, right? We knew it converged at 0, right? Because, you know, we always have that possibility. The question is, how far away from 0 can we range? We could range infinitely far away, but that's not the case for this guy. You can only go 1/3 away from 0, right? So the domain of this guy is restricted, yeah? It's not infinite. Okay, so we know we have convergence here between 1/3 and negative 1/3. We know what else? We know if we're smaller than negative 1/3, what has to be true? Divergence, right? Because we would have a greater than 1, and the root test would tell us it's greater. And what about this out here? Also divergence, right? If x is bigger than 1/3, right, then 3 times the absolute value of x will be bigger than 1, and root test will tell us divergence. What don't we know, right? We don't know what happens at each of the endpoints, right? When x is negative 1/3 and when x is 1/3. So that's what we now need to figure out. Yeah? Okay? So we must test the endpoints separately. Okay? So what are the endpoints? X equals negative 1/3 and x equals 1/3. The endpoints of this interval. We don't know. Either both endpoints could be included, both could be excluded, or one might be included and one excluded. Okay? So, you ready? Let's do that. Here we're about to do the more complete job, right, with the endpoints. You can compare that to what the book does. What the book does is more kind of the way you would think about it maybe when you're doing the online portion and you don't have to justify everything and you want to have instincts, right? But what we're going to do is how you justify stuff, okay? So let's do, consider the x equals negative 1/3 endpoint. Okay, that's what we're going to start with, okay? So we're trying to decide, does this series converge when x is equal to negative 1/3, right? So if x is negative 1/3, then what am I going to do with that x? I'm going to plug it into my original series. Here was my original series, right? I'm going to put a negative 1/3 in for x, right? So what am I going to have? I'm going to have a series sum n equals 0 to infinity of minus 3 to the n times, what is x? Negative 1/3 to the n, right? X is negative 1/3, so that's raised to the n, all divided by the square root of n plus 1, right? Okay. So now what do? Before I do anything, I algebraically simplify. So you guys tell me with rules of exponents, right? We've been pounding this all semester. The denominator stays the square root of n plus 1. The numerator, make sure we understand what the rule of exponent is, right? A to the n times b to the n is a times b to the n, right? Yeah? And what is 3 times negative 1/3? Good. So I'm not doing anything, I'm just doing like arithmetic, right? Negative 3 times negative 1/3 is just 1. Yeah? Right? These guys cancel, the negatives cancel. I've got 1 to the n over the square root of n plus 1. And what is 1 to the n? It's always 1, right? That's where we started in chapter 11. 1 to the n is always 1, right? So I've got 1 over the square root of n plus 1. Yeah? That is what this series is when x is negative 1/3. So the question of does this guy converge at this endpoint is the question of does this series converge? What's your gut instinct for 1 over the square root of n plus 1? Okay, so good. The gut instinct is that this guy diverges. The sum, n equals 0 to infinity, of 1 over the square root of n plus 1 diverges. Right? Why? Why is that our gut? Because we know the sum that n equals 1 to infinity, right, of 1 over the square root of n is what type of series? Good. It's a p series with p equal to, yeah, good, 1/2, n to the 1/2, right? So what do we have? Our b sub n is 1 over n to the 1/2, yeah? P is 1/2. Tell me about p series. What's the rule for p series? If it's less than 1, it diverges, right? So my comparison series diverges, yes? Okay? My comparison series diverges. All right, so now what? That's our guess. So if we're doing web sign, right, we just, we see this series and we, choose diverge and move on, right? But if we are, if we're doing work for justifying that we understand what's going on, then you still got to do more, right? This isn't enough. You've either got to decide what test you're going to use, comparison test or limit comparison test, right? Okay? So, now, tell me, can you use the comparison test, right? So your an is 1 over the square root of n plus 1, and your bn is 1 over the square root of n, right? This is your comparison series, okay? This guy diverges. Is this bigger or smaller than that? Same numerator. This guy has a bigger denominator, so he's smaller. He's smaller than this. Therefore, comparing with the comparison test with something that's bigger that diverges tells you nothing, right? Nothing. So you got to use which test? Good. The limit comparison test, where you're looking at the limit as n goes to infinity of an over bn, right? And so for us now, right, this isn't the an we're talking about. We're talking about the specific an when x is negative 1/3. So we're doing the limit as n goes to infinity of 1 over the square root of n plus 1 divided by 1 over the square root of n, right? Because this guy's our comparison series, which you know diverges. What is this limit? Algebra says it's the limit as n goes to infinity of the square root of n over the square root of n plus 1. Limit. Algebra also says this is the limit as n goes to infinity. I'm going to do 2 steps at once, right? Well, I won't. Square root of n over n plus 1, that's just 1 step, right? Okay, that's just rules of square root and fractions. Then what do? Limit as n goes to infinity is going to come inside. Square root is going to be out here, yeah? And then since we have infinity over infinity, we do our favorite trick, which is divide everything by the highest power in the denominator, which is n. So we get 1 over 1 plus 1 over n, yeah? This guy goes to what? oh, 0. And this becomes the square root of 1, right? Which is 1. What were we doing? Oh, we were doing the limit comparison test, right? 1 is a great result for the limit comparison test out of a limit, right? 1 is a terrible result out of the root test for a limit, right? Okay? But 1 for the limit comparison test is awesome because what do we need? We just need this to be not 0, right? Or positive. And since that's positive, therefore, what can we conclude from the limit comparison test? The limit comparison test, which took the limit, right, says what? This guy diverges because the comparison series diverged. Yeah, diverges. Okay, so what do we know? Do we have convergence at this endpoint? No, right? Okay, no convergence there. So negative x equals negative 1/3 is not in the interval of convergence. Okay. So what do we know about the interval of convergence? We know that 1/3 is not in there, and we get out to 1/3, and we just don't know whether to put a parenthesis here or a bracket. Is 1/3 included or not included, right? So now what do we have to do? You got it, one more. Do the x equals 1/3 endpoint. All right. Consider now x equals 1/3 endpoint. Okay. So for x equals 1/3, our original series becomes now what? The sum n equals 0 to infinity minus 3 to the n times 1/3 to the n, right? Putting 1/3 in there for x, divided by the square root of n plus 1, right? Okay. Now what do we have? Okay. This guy is the sum n equals 0 to infinity of, minus 3 to the n, right? Minus 3 to the n, yeah. What is minus 3 to the n times 1/3 to the n? Good. Minus 1 to the n, right? Just same thing we just did up there, right? Okay. Although now you don't have minuses that cancel. So you've got minus 1 to the n from that product. What do you have down here? Square root of n plus 1. This is the series we want to know. Does this series converge? Absolutely. That's what we usually do when we have negative things. We look for absolute convergence. So do we have absolute convergence? No way, right? Because what is the absolute value of this series? It's this one we already looked at. Yeah, so if you choose which endpoint you do wisely, you might have some good information. All right, which one you do first, okay? Depending on how it works out in your problem. So this guy does not converge absolutely because we know the absolute value diverges. We just showed that, okay? So the answer is no, okay? So absolute convergence, out. What do we look at? But wait, right? But wait. It's what type of a series? It's an alternating series. What do we know about alternating series? We have a test for convergence, conditional convergence, when the series doesn't convergence, but not absolute convergence, right? Okay? You can't change the negatives to positives, but does the actual series itself converge, right? Okay, so what do we do, right? So does this series converge? Conditionally then. So are we conditionally convergent? Does it still converge, the series? Okay, even though the absolute values of it doesn't converge. So, let's check. What are we going to check with? The alternating series test, right? Let's do the alternating series test for what? The sum n equals 0 to infinity minus 1 to the n over the square root of n plus 1, right? Okay? So what are the bn's here then now? Well, what did that mean with the alternating series test? It just meant the absolute value, right? That's what it meant. You ignore the negative 1 to the n, and then we just look at that guy. And what has to be true about these guys, right? Are these decreasing? Well, what's one way to say they're decreasing? B sub n plus 1 is less than B sub n, right? The other way would be to turn this into an x and take the derivative and show the derivative is negative, yeah? But this one's super easy with the inequality, right? Why? Because what is B sub n plus 1? If this is B sub n, what is B sub n plus 1? You tell me? 1 over, put an n plus 1, where's the n? The square root of n plus 2, right? And what is B sub n? B sub n is 1 over the square root of n plus 1. And can we say that this guy's less than this guy? Yeah, we sure can. But if you just say that and don't say why you can say that, then I don't know that you know, right? So how do you convince me you know? Oh, look, right? Same numerators, right? The numerators are exactly the same, right? This guy has a bigger denominator. N plus 2 is clearly bigger than n plus 1. Square root of n plus 2 is clearly bigger than square root of n plus 1. Okay, so obvious. It's got to be obvious. Same numerators, bigger denominator here means smaller fraction. So you've got to convince me that you know, right? That is the alternating series test. Check for decreasing, right? Again, the other thing you could do is call that an x and write it as b of x is the square root of x plus 1, or x plus 1 to the negative 1/2, right? Take the derivative properly and make that argument. Okay, what else should we check, right? And, right? Okay, you got to have the limit as n goes to infinity of the bn's 0. That's obvious. Here, right? That limit is 0. Okay. If that limit wasn't 0, then the divergence test would have told us this guy didn't diverged to begin with, and we wouldn't have even been here. But what happened? Did we pass the alternating series test? Yes, indeed we have. And so therefore, what can we say about this guy? Is the series conditionally convergent? Yes, it is. Yeah, right? This is conditional convergence. Again, it looks like an alternating harmonic series. So if you were on a WebAssign online part quiz, you would have the instinct when you saw it to know, hey, that looks like an alternating harmonic series. That's going to be conditionally convergent. But if you're doing written work where you're justifying everything, then you're showing your work, right? Okay. So what do we know? Do we have convergence here at 1/3? X equals 1/3. Look, we knew what we were doing because we had it labeled. Yes, indeed, right? So this guy gets colored in, right? Okay, we have convergence not at that left endpoint, but yes at that right endpoint. So what does that mean? Here is my interval with the bracket, right? The interval convergence of this guy is minus 1/3 less than x less than or equal to 1/3. So it's okay to put 1/3 in there and have this guy converge to the finite sum. It's not okay to put negative 1/3. And then you can put in anything in between, but nothing outside. Yeah? Is that cool? That's it, right? So I think that was sort of nice just to be able to take one example and really see pretty much everything we've been talking about for the last couple of weeks all come together in the exact same place, right? Okay, that was super nice. Let me just do one more thing for you guys. Suppose you have, suppose we have a power series. Expanded about a equals 2. So we know this power series has to converge at 2. Okay. Question is where else does it converge, right? So suppose we know this this power series converges for x equals 5. Right? Suppose we know it converges at x equals 5. Then what do we know? Well, we know the radius of convergence then is at least 3. Right? Okay? So we then know that we have to be able to go 3 units in that direction as well. So what is 3 units in this direction? What will this be? 2 minus 3, good, -1. Now, I know this guy converges for x equals 5. Do I know it converges at -1? No, I don't know anything about -1, okay? But I do know that I have convergence from -1 to 5. Now, if, for example, I knew it converged somewhere else, right, further out this way or further out that way, then I'd be able to expand, right? Does that make sense? Okay. Or if I knew it diverged somewhere, I knew I couldn't go beyond, right? Okay. So I know this guy, suppose I know that it diverges at, suppose I know it diverges at 7, right? If it diverges at 7, well then I know the radius of convergence can't be any bigger than 5, right? If it diverges at 7, then it diverges for everything else that way, and it diverges for everything, if I went 5 this direction, right? So 2 more, right? Then I know I've got divergence that way. But I really don't know anything else about the in-between. Does that make sense? Yeah? And that's all the content of our conclusions of our ratio and root tests. Those are pretty awesome tests, right? We proved the ratio test, right? Homework, you proved the root test, right? Okay. All right, that's pretty much all for today. Maybe that example went on a little longer than what I intended, but hopefully that might clear up some of the confusions I saw as I was grading test 2, and just thinking about what justifies what and what is what, right? Okay, so make sure you're naming these series as you're talking about them, because otherwise you're just going to get super confused. And why do we not want to get super confused? Because we move on to next week's, our last week of classes, is the culmination of everything we've been driving at, where we see why power series become such an important thing. All right, have a great end of your weekend.